This is Chemistry, Module 12, Review Questions. Number 1, define pressure and name 3 units to measure it. So pressure is force applied over a given area. You could measure in pascals or kilopascals, newtons per meter squared, pounds per square inch, torr, millimeters of mercury, feet of water, and those last two would be in terms of a barometer. Number 2 says write Boyle's law in your own words. So it's important and required for you to give the caveat for Boyle's law as well as the equation, or something that describes the equation. So as long as temperature is constant, that's the caveat, has to be there, then the product of pressure and volume is constant. So PV equals K would be fine, as long as temperature is constant. Or you could say pressure and volume are inversely proportional. One goes up, the other goes down, right? Number 3, which of the laws that you studied in this module leads to the Kelvin temperature scale? So if you extrapolate data from Charles' law, regardless of the gas that you're using, whether it's hydrogen gas, nitrogen gas, a mixture of gases, regardless, when you extrapolate the data from Charles' law, which you guys are going to do in the lab, you find that kind of all the data points converge at negative 273.17, I think, ish, Celsius, which is 0 Kelvin. So extrapolating Charles' law, and so they defined that kind of low point as absolute 0 and defined it as 0 Kelvin because we can't have a 0 in a denominator, or we have an undefined situation. And so since temperature appears in the denominator of many equations in gas laws, we needed a scale that never reached 0 in that denominator, so Kelvin. Number 4. What general rule must a careful scientist follow when extrapolating data? So Dr. Boyle in the book says you need more data than you extrapolate, right? So if you have like data over 50 degrees Celsius range, then you shouldn't go 50 degrees in either direction. I say you should not go past 10% of the data you have. Right, so like if I have data over 100 degree range, I wouldn't even go 10 degrees on one end or the other of that data. And so I am more conservative than the textbook would indicate. I really am not comfortable ever extrapolating more than 10% on the ends of data. But when we do extrapolate in the lab, in class, we go way beyond even like our range of data. Like if we have 70 Celsius points, we still go way beyond 70, and we actually do still find that our line points pretty close to absolute 0. So even though we extrapolate far too much, it still works. I would not extrapolate very much at all as a scientist, though. I would look for ways to extend my data so that I can feel more confident about extrapolating a tiny bit on the ends. All right, number 5. What are properties of an ideal gas? Molecules are small compared to the volume that they take up, right? So one mole of gas, ideal gas, takes up 22.4 liters, right? So that's a huge, huge volume for a tiny amount of gas, 1 mole of gas, right? Number 2, the molecules or atoms need to be so far apart they don't experience attractive and repulsive forces between them. Number 3, you need to have elastic collisions between the gas molecules and the walls of the container. So, number 6, under what conditions do gases behave ideally? So near standard temperature and pressure, right, which is 1 atmosphere, I think, to 3 sig figs and 0 Kelvin. When you're dealing with temperature, close to that or higher is fine. And when you're dealing with pressure, close to that or lower is fine. Remember, gases behave more ideally when temperature is high and when pressure is low. And when I say close to that, I mean like 1.2 atmospheres is fine, maybe, but like past that, and like 0 or 0 Celsius is fine. Not much below that. Anything above that's great. Okay. What is standard temperature and pressure? So STP is 273 Kelvin and 1 atmosphere. Both of those 3 sig figs. And remember also standard conditions, which is 298 Kelvin and 1 atmosphere. STP and standard conditions are different. Nobody wants to work in an STP lab. Standard conditions is comfortable room temperature. 8. 2 steel containers of equal volume contain 2 different gases at the same temperature. The first has 1.3 moles of N2 gas and the second 1.3 moles of SO3 gas. Compare the pressure in the 2 containers. So Dalton's law tells us that it doesn't matter what the gas consists of. If it's nitrogen molecules, sulfur trioxide molecules, even tiny little hydrogen molecules, or even a gas that's made of bigger molecules. If they're under the same conditions, they're going to have the same amount, the same number of moles. So the pressure in this case is the same because they're in the same volume with the same number of moles and the same temperature. Number 9, a liquid temperature is lowered from 50 Celsius to 10 Celsius. Does the liquid's vapor pressure increase, decrease, or stay the same? So vapor pressure comes from, like, say you have a cup sitting out of water, right, and it's going to evaporate. That means that some gas is, or some of the liquid is becoming a gas at any given time, right? And so that causes a vapor pressure because that gas is evaporating. And so with water, the higher the temperature, the higher the vapor pressure because more will be evaporating. So increasing the temperature will increase the vapor pressure. In this situation, we are decreasing the temperature, so we're going to decrease the vapor pressure. There's a chart in your book someplace of vapor pressures at given temperatures. Generally, we use that chart to help us when we're collecting a gas over water. So if you're producing a gas from a reaction, like, you know, when we produce carbon dioxide from a vinegar and baking soda reaction, right? Or if I produce hydrogen from like throwing a metal in some acid or something, what I could do is channel the gas that's being produced, through a thin tube out of the container it's being produced in, and then to try to collect it, right? It's hard to fill like a test tube or something. So what you do is you just take the tube where the gas is coming out, put it under water, and then fill the thing that you want to collect the gas in with the water. And then the gas will force the water out that you're collecting, and then it will be filled with gas. So when you collect a gas over water, which is what you're doing in that case, that technique, you get some evaporated water molecules in the gas that you're collecting. So your gas will be contaminated with some humidity, basically. And so you have to subtract out the vapor pressure of the water at the temperature that you've collected it before you can understand the pressure of the gas alone. But Dalton's law tells us it's a simple matter of adding up all the vapor pressures of all the gases, and the sum total of them is just the pressure that you have. So it's pretty easy. And those charts give us a good idea at a given temperature. Number 10, the mole fraction of nitrogen gas in compressed air is 0.78. If you have 1,000 molecules of compressed air, how many are nitrogen molecules? So 0.78 in this case is kind of like if you just took a test and you, let's say you got 14 out of 15 on your test, right? And I think 14 out of 15 is like a 93.3%. But if you type 14 divided by 15 into your calculator, you actually get that, right? And so that 0.78 in this problem is kind of like a percent that's expressed as a decimal. So basically 78% of the molecules are nitrogen, so majority, right? So the majority of those 1,000 molecules are going to be nitrogen. So if I did basically 0.78 times 1,000, I would get 780. I can keep two sig figs, so I'd have to basically use scientific notation. So I would express 780 like this. 7.8 times 10 to the 2 is 780 molecules of N2 gas. So that's the review questions. I'll be back with practice problems.